Hello everyone, my name is Amey. Welcome to this session on data lakehouse performance at scale. Today I'll be talking about how we achieve up to 85% fast analytics by introducing a distributed caching layer on the top of our lakehouse. I'll walk through the motivation, the architecture, the performance results, how this translates into business value. Over the next few minutes, my goal is to give you a concrete idea uh, that you can take away to your data platforms. Uh, so before we start, let me provide you with a brief introduction about myself. So I am a software engineer based in Seattle, Washington. Over the past 11 years, I have worked across enterprise domains, including e-commerce, automotive, and telecommunications, primarily focusing on building and scaling large distributed systems. My academic background includes a master's in management information systems from the University of Illinois and a bachelor's in instrumentation control from Manipal University. Professionally, my experience spans leading microservices modernizations on AWS, scaling checkout systems at Zulily, architecting connected vehicles and autonomous ride-hailing platforms at Ford Motor Company in Detroit, and some exposure to 4G systems, delivering 4G systems at Telefonica O2 UK as well. Across these roles, one pattern had been consistent. Performance at scale is never optional. So when data systems slow down, entire organizations feel the impact. Today's talk directly builds on that theme. So moving forward, with that context in place, let's jump into why Lakehouse performance matters so much right now and in today's age. So let's look at whys. Let's start with the whys. In many organizations, the lakehouse is the central nervous system for data, for teams like analytics, for use cases like dashboards, ML features, and ad hoc explorations. They all run through data lakehouse. As data volume and concurrency grows, the performance isn't a nice to have per se. It directly impacts how quickly the business can make decisions. Uh, if dashboards, for example, update slowly, analysts would wait for minutes for queries, or ML pipelines would crawl, and the organizations lose agility. This results in people stopping to trust the platform, and teams work around it with local extracts and shadow systems. We often assume that scaling compute horizontally will solve this, but as data sets and snapshots grow, IO overhead, deserializations, and repeated work become the true bottlenecks here. Uh, Lakehouse performance, especially around caching and data access, becomes a first class design problem, and it's not just a tuning exercise. So let's talk about the challenges in large scale analytics workloads briefly. Uh, in our environment, we ran into several classic challenges that many of you may recognize, right? First was the excessive input and output, what we call as IO. Query engines repeatedly scanned the same data sets and partitions from cloud object storage. Second was serialization overheads. That was converting data between formats and internal structures, burned a lot of CPU. We also had a heavy joins and aggregations when the concurrency was high, and workloads fought over the same underlying objects, leading to unstable latency. On the top of that, snapshot based updates meant that data was constantly evolving. So even when we try to cache, keeping the cache fresh, and correct was non-trivial. So these challenges created an environment where even modern engines struggle under realistic load. So some of the key contribution of this work, given those challenges, this work focuses on set of concrete contributions. To start with, we introduced a multi-tier rather distributed caching architecture that significantly reduced repeated I/O. Second, we started on Apache Arrow as our in-memory format, which enabled vectorized execution and efficient data sharing. We also built a snapshot aware invalidation mechanism so that cache correctness tracked Lakehouse snapshots. We also added a ML-driven cache warming strategy to predict which data sets should be hot before queries would arrive to us. And lastly, when we implemented optimized cache allocation policies to make the best use of limited cache resources. To summarize, together these pieces formed a performance layer that sits cleanly on the top of Lakehouse without breaking its abstractions. Moving on. So the gist of this slide is to show you a conceptual modern lakehouse architecture. At the bottom, you typically have an object storage like AWS S3 or GCS or similar, holding immutable data structures or immutable files. On the top of that is the tabular format and transaction layer like Delta Lake or Apache Iceberg, which manages snapshot and metadata for you. On the top of that, you have a compute engine, something like Spark and Flink, or Apache Spark or Apache Flink, or warehouse style engines that query this data. Finally, at the top layer on this, you have dashboards, BI, ML pipelines, APIs that depend on all of this. The challenge is that compute and storage are decoupled. That's great for elasticity for sure, and it's great for cost as well. But it means that every query has to reconstruct state from files and logs. So our primary work is about optimizing the boundary between compute storage with smart caching and while staying compatible with this architecture. Here we introduced a 3-layer caching architecture we used to accelerate Lakehouse workloads. Tier 1 for us was local executor cache. This was data cached directly in the memory of compute nodes running the queries. It's extremely fast, but it's also ephemeral. Tier 2 here was distributed in-memory cache, distributed coordination, a shared cache across executors, which was used for data sets that are hot across many queries and jobs. Lastly, Tier 3, which was SSD-based backed cache, a persistent cache on fast local storage surviving processes, restarts, and job boundaries. The core idea here is that data flows through these tiers based on access frequency and cost. Right? Hot, frequent access data sits in memory. Colder but still valuable data may reside on SSD, and everything else other than this falls back to reading from the object storage, which will be slower, but you have to go there at the end if nothing is available to you. By routing data intelligently through these levels, we dramatically reduced cold start costs and stabilized performance under concurrency. So why did we use Apache Arrow? We chose Apache Arrow as the core in-memory representation for a few key reasons. First was Apache Arrow is columnar, right, which is ideal for analytical workloads that performs scans, filters, aggregations over columns rather than rows. Right. Second is Arrow is designed to zero copy interoperability. What that means is different systems and libraries can share Arrow buffers without constantly serializing and deserializing data. What that meant for us was less CPU spent on data movements and more CPU spent on actual computations. Lastly, Arrow enabled vectorized execution for us, operating on batches of values at once, which makes much better use of CPU cache and modern processor instructions. So by aligning our caching layer around Arrow, we cut out multiple layers of conversion overhead and multiple queries, and we reduced the time significantly for these queries. So let's talk about snapshot aware invalidation. As we all know this, a cache is only as good as its freshness. In a lakehouse, data is updated through snapshots. You do new versions of tables. The tables are created as files are added. removed, and rewritten. If your cache doesn't understand snapshot, you risk serving stale or inconsistent data. We built a snapshot aware invalidation systems that tracks which cache blocks map to which table versions. So when a new snapshot is committed, the system identifies exactly which partitions or files have changed and invalidates only those cache entries. So what this gave us was the best of the both worlds, right? Correctness, because we never serve data from the wrong snapshot. And secondly, what we got out of this is efficiency, because we avoided throwing away the entire cache when only subset of the data had changed. So ML driven caching warming strategy is another piece here. We noticed strong patterns in how data was accessed. Things like morning dashboard refreshes, hourly reports, pardon me, nightly batch jobs, periodic ML feature generation. Instead of waiting for queries to match the cache and then learn, we started predicting which tables and partitions would need, the data next. We also used lightweight models to forecast upcoming access patterns and pre-warm the caches, especially tier 2 and tier 3 before heavy workload kicked in. So in practice, what this meant for us was dashboards were loading faster at the business hours. Uh, Another advantage that we got of this for was scheduled pipeline started with warm data instead of paying cold read penalties. And lastly, the platform felt more interactive even when workload that used to be batchy and slow, right? So moving on, cash, as you know, is a scarce resource, right? And how you allocate it matters a lot. It is one of the costliest things on your infrastructure as well. So we implemented the adaptive allocation policies that consider these above mentioned below mentioned points. First was access frequency, right? How often a data set or partition is read. Second was query cost. What is the expense or how expensive it is to recompute or reread from storage. Third was data size, right? How much space a block consumes in the cache. And lastly, the cross team usage, whether multiple teams or job rely on the same data, right? Based on these signals, the system decides which data deserves premium placement in memory tiers versus SSD, right? And which entries should be evicted first. Over time, these policies significantly improved cache hit rates and helped us ensure high value workloads uh, always had priority access to fast data. Some real world production environment, we had a mix of workloads in our production environment. For example, we had business intelligence dashboards, which were used for operations, merchandising, and financing. We had vendor supply chain analytics, which were, again, managing onboarding of vendors, inventory that we had in our warehouses, and shipping of our orders onto our customers, and ML pipelines for personalization, recommendations, and forecasting. Each of these uh, had a different access pattern and performance expectations, but the caching layer needed to serve them all essentially. Uh, the true test here came to us during peak traffic events, primarily during, as you understand, Black Friday events, because Black Friday is pretty big during e-commerce sales. Sales, promotions, seasonal spikes. Even under these conditions, the new architecture kept latency stable for us and prevented the kind of performance degradation that used to frustrate user and on-call engineers. So here we see the concrete impact across uh, a broad set of workloads. We measured up to around 85% fast analytics end to end. That includes performance in query latency, especially for recurring analytic workloads, CPU utilizations, which was thanks to Arrow-based vectorized executions, and storage I/O, because many query avoided hitting object storage entirely altogether. Heavier queries involving joins and aggregations saw some of the biggest wins. Workflows that previously took minutes completed in seconds for us. this wasn't just a minor speed up, right? It fundamentally changed how interactive the Lakehouse felt to our users. So driving financial value here, performance is great, but at the end of the day, what we really care about is business impact and ROI. So fast analytics for us meant teams could make sensitive decisions earlier, right? Analytics productivity improved because they weren't stuck waiting for slow queries, and more importantly, compute and storage costs, which were more controlled since we reduced redundant work and avoided overscaling cluster to compensate for the inefficiencies in the systems. When you combine these effects, better decision making, higher productivity, and lower infrastructure waste, the return on investment for caching work is very compelling. It becomes much easier to justify the ongoing investment in performance engineering. Of course, when we got to there were some operational challenges. Early on, we ran into multiple invalidation edge cases where subtle bugs would cause tail data if not handled correctly. There was memory pressure and eviction storms, when multiple hot data sets competed for limited in memory cache, essentially. Uh, the need for strong observability metrics and dashboards for hit rates, miss reasons, and version mismatches. To mitigate this, we invested in instrumentation to track cache behavior in detail. We tuned thresholds for policies iteratively based on real traffic. Over time, these improvements turned the caching layer from something experimental into a stable, reliable piece for our data platform. So, going forward from here, looking ahead, there are several promising future directions. One is deeper integration with query optimizer, so the optimizer can reason directly about cache state when planning the execution of the queries. Another is exploring cache closer to the metadata and the transaction layers, accelerating not just reads but also snapshot and log access. We are also interested in adaptive compression strategies for Apache Arrow buffers, and potentially using reinforcement learnings to continuously optimize the cache allocation and warming policies based on the live feedback that we get. The long term goal here for us is simple: push the lakehouse to closer to true interactive performance at scale, right, without losing the flexibility, the cost advantages, and that attracted towards the lakehouse model in the first place. Uh, so that brings us to the end of this talk. Thank you for spending your time with me today. I hope this walkthrough of Lakehouse performance at scale, distributed caching, and real world production results has sparked some ideas that you can apply in your own environment. Thank you.